So, uh, uh, so hello everyone, this is Sutto. Today I will present the analysis of three research paper as a part of research writing assignment. So in this presentation, I will mainly discuss the structure and the writing style of three research paper related to the organic optoelectronics material and laser emitter mainly. So the goal of the assignment uh, the goal of the assignment to analyze how the research paper are writing or structure. So the main point I'll discuss here whether the introduction follow the standard anatomy of the research paper and reverse engineering the research and development section and separating result from the discussion. How the author compare these work with the previous literature, and finally the difference between abstraction and conclusion section. uh, so basically a well written introduction usually follows the sequence, the first big picture and background motivation, and then what is the already known portion, current problem, knowledge gap, why the gaps matter, and what uh, what the paper does. So, my first paper, the overview of the in-depth effect on solution possible deep blue lasing material with the low amplification spontaneous emission threshold. So basically, in this paper, they try to demonstrate the laser technology is important for the many application field such as mm, uh, telecommunication, sensing, medication, diagnostic, or organic laser material are again effective because they are low cost fabrication, flexible, and most important solution possible. So that's why the people are trying to focus currently for organic semiconductor materials or organic lasing materials. So now, the introduction section of this paper implies the author explain the importance of the laser technology first, and then they discuss the advantage of the organic laser. Then they explain the current limitation of the blue laser emitter. After that, they identify the knowledge gap and etc. So now the big picture motivation for this paper, uh, has implies that laser technology are broad application I have discussed already in the field of medicine, telecommunication, and again the organic laser are attractive for alternative of lightweight material as it is very flexible, low cost fabrication, and tunable property, which is most important to enhancing the photophysical property, which can be done in organic materials only because we can tune different type of donor group, the more by different type of donor group in the ferrant molecule, so that we can achieve the best photophysical properties. And then now the what is the known in this topic. So the known already known portion is the organic laser system has been already studied in basically in dye-based laser, and many organic molecule can exhibit the AAC emission, uh, AAC emission, and in conventional molecular designing for the organic laser is that we can increase the conjugate length. Basically people are focused for increasing the conjugate length, and which implies the best PLQ or reducing the non-radiative decay. So these are the some method people are trying to achieve the best materials, but the problem here is uh, 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 achieving the efficiency deep blue emission is quite difficult, or deep red emission also difficult. So as people are trying to focus only the conjugate length, but at the same time people are forget about the um, oscillating strength of the molecule. So we need to focus on balance of conjugating length and oscillating strength for this material in basically TADF type materials. So this issue reduce this issue reduce the optical gain and prevent the efficient lasing. So now the knowledge gap is the only a limited number of deep blue organic laser chemical are currently known. There is a insufficient understanding how the molecular end group influence the optical gain properties, and uh, and currently the role of how end group influence the olefinyl system, which has not been studied yet properly. So now the why the group matters, because ultimately the deep blue emission is needed or essential for full color laser display, and at the same time optical communication system and sensing technology, etc. And improving the deep blue organic laser materials would allow the development of organic laser diode, low threshold photonic device, etc. So now the what the paper does here, the author designed or synthesis two molecule, olefin-based molecule, and they have showed how the in cap with carbazole or phenyl carbazole group influence the overall molecular properties. And they did the different type of photochemical studies that like the optical transition, photochemical efficiency, AC measurement, and uh, they did the theoretical studies also. The new molecule exhibit their molecule exhibit they showed the luminescence quantum yield nearly 90%, and which is very attractive, and very high radiative decay also they have observed. And the most important, they got the deep blue emission and extremely low AC threshold, nearly 1 to 1.5 microjoule per semi square. So now why the deviation from the standard structure? So the introduction contain a long historical discussion of the organic laser compared to many modern paper. The author emphasized the technology application of laser before the narrowing the specific research problem. Some performance result are briefly mentioned in earlier texts. Uh, and now the logic of and now the reverse engineering paper. So now we analyze the research and development strategy. The author designed a rigid olefin laser chromophore. They attach a carbazole and phenyl carbazole end group, carbazole and phenyl carbazole end group, and the reason behind the design these carbazole groups, the strong electronic donating ability. Okay, strong electron dominant which influence the optical transition probability, emission efficiency, and AC measurement. So they have did the structural characterization by the NMR, mass thermal analysis, that means TGA or etc. And photophysical studies also did UVPL and radiative decay rate, photoluminescence quantum will measure, and AC measurement they did, and they got the threshold energy of 1.0 to 1.5 microjoule per meter square, which is very great. Now the result, so ultimately they got the the molecule shows a very high photoluminescence quantum, which is already I've told, and the radiative decay is extremely high, 1.35 to 10⁻⁹ second inverse, and they got the deep blue emission is observed. The material shows the excellent thermal stability and strong photophysical properties and low trip triplet quantum yield. That means uh, uh, that means the exciton is 100% over the single state only. So the benchmark novelty of this paper is they got the threshold 1.0 to 1.5 microjoule per meter semi square. But earlier deep blue organic emitter typically have the AC threshold higher than the 5 to 10 microjoule per semi square. This is the key benchmark novelty. Now, the similarity between abstract and conclusion. Both sections emphasize the design of in-gap olefin laser comfort, and both sections confirm that molecule exhibit deep blue amplification, spontaneous emission, and section highlight the photoluminescence quantum efficiency of the material, and both section shows the importance of molecular design strategy for the laser materials. Now the difference is abstract provide a concise summary of the studies and highlight the key experiment of such as photoluminescence, quantum yield, radiative decay, C threshold value, etc. Um, uh, but the conclusions offer a broad interpretation of the result. They explain how the in-group engineer enhance the photophysical properties of optical transition, and they discuss the significance finding of the figure of organic laser development, and overall they emphasize the potential impact of the work on photonic and optoelectronic technology. So that's all the first paper. Now my second paper. Mm, the title is a new organic laser material designed towards the ultra low amplified spontaneous red emission and ultra bright electroluminescence. Uh, uh, so basically, uh, they in the introduction structure, uh, the second paper studies the organic semiconductor laser materials based on the Sivalactode dimer, and organic semiconductor laser are promising because they are allowed the tunable emission wavelength and flexible molecular design and low cost fabrication, which I've already discussed. The same thing they here also showed. And introduction. The introduction again for the classical structure. So um, uh, they then try to explain in that means try to explain the difficult of absolute electrical pumping, lasing, etc. I mean, here the picture modification they shows again why organic semiconductor materials important, low cost fabrication, etc. They try to show, but the important is what is already known for this paper. So already the optical pump organic laser have been successfully demonstrated already. The key parameter controlling laser performance include the emission cross section, radiative decay rate, PLQY, and excited state lifetime. Okay, and the several molecule design strategy have been already attempted, like conjugate, increasing the conjugate polymer structure, or cross-link framework, and peripheral substrate modification. But the main problem is achieving the electronic pump organic resin is still extremely challenged. Major limitation includes the optical losses of in devices, triplet excitation accumulation, and excitation annihilation. The major problem. Mm. And efficiency roll off also the major problem at the high current density. So the knowledge gap is the existing organic laser material cannot simultaneously satisfy the multiple performance requirement, such as the low lasing thresholds, high radiative decay rate, low triplet yield, and strong electroluminescence and high photophysical stability. The why the gap matters, because the efficient electronic form organic laser would revolutionize the optical device, integrated photonic circuits, and display technology, etc. Now the what the paper does here, they basically design two dimers. So one is phenyl linker based dimer, and second is fluorine linker based dimer. So both these dimer the studies or investigators how the dimerization and conjugate length affect the laser performance ultimately. So in terms of oscillating stand or photophysical behavior or simultaneous emission cross section and AAC threshold, they also measure. And uh, and uh, and here the deviation from the standard introduction structure. The introduction show two major deviation. First, the author discussed the device electrical strategies before preventing their molecular design application, and second, some photophysical equation are introduced earlier than usual. This deviation improve clarity because the explanation explain the physical basis laser performance, and they justify why the oscillating stand and relativity are crucial for us. So reverse engineering uh, section. So basically, the design strategy is based on the molecular dimerization. So the molecular connected using different linker like the phenyl linker or fluorine linker. The idea is the dimerization can increase by the absorption state, radiative decay, or AC threshold, etc. So now the they performed experiment. They first synthesize the materials, that is for CYC monomer, which is parent molecule, and they did the phenyl linker and fluorine linker, and then they did the photophysical characterization like thermal energy, electroluminescence measurement, and the theoretical calculation also they did DFT studies, and they finally they did the AAC measurement, and OLED fabrication also did. So and after the OLED fabrication, they got the OLED wildness ultimately 7.1 into 10 to the power 5 candle per meter square, and AAC threshold is quite good for all dimer and monomer also. And the dimer shows 250% increase the absorption exciton efficiency coefficient, which increase the oscillating stand efficiency, oscillating stand, and radiative decay rate also improve. So, uh, so, uh, so the comparison between the previous literature report, the benchmark performance is the reported AC threshold is 4.5 microjoule per meter square, is the ammo is among the lowest reported for the deep red organic emitter. And the now the comparison of abstract and conclusion both emphasize the dimension strategy for the improving organic laser material. Both highlight that the to 50% increase the oscillating strength, and each state that dimer shows the ultra low AAC threshold, and both mention OLED performance also. But the difference is abstract and conclusion. Uh, So basically, abstract provide a concise summary of main result, which highlights oscillating strand enhancement, AC threshold value, and OLED brightness. But conclusion provide a deeper interpretation of this result. And explain how the role of conjugated linker and dimerization influence to gain the optical or to enhance the optical properties like the radiative decay rate, optical gain, and triplet suppression, and discuss the future potential organic semiconductor laser, that is the future scope. So now, uh, in third paper, based on the organic radical emitter, which is a advancement of the organic semiconductor materials. So basically, here in they introduce introduction begin with the OLED fundamental, and then it explains the spin statistics problem, why the radical based molecule is based, or open system is molecule is based on the closed system molecule. They have showed a clear idea about that, because there is a there one type of energy state is possible, that is doublet, so that we can get the maximum uh, population over the excited state, which is double state only. So there is no loss or distribution of population over a singlet triplet, which is happened in case of TADF or fluorescence or phosphorescence type material. But when we talk about the radical system, so only one type of energy state are possible, which is dimer. So the doublet. So the transition happens only doublet excited state to doublet ground state. So in theoretically, we can get the 100% quantum yield. So in introduction section also they mention the same thing, the overview of the OLED fundamental, and why the phosphorescence medium and TADF is uh, TADF like materials is what is the disadvantage, and the big structure also shows this type the same thing. The electrical excitants create the 25% excitant, that 75% excitant over the excited state for case of closed cell molecule like TADF, fluorescence, and etc. But the for the radical system, the problem is, despite of the theoretical advantage, the most organic radical show the very weak photoluminescence, and mainly the radical molecule often exhibit low absorption, poor emission intensity, and strong red non-radiative decay. Uh, Now the what is already known. The known is to overcome the singlet triplet inhalation, which is the main issue for the closed system material like TADF, fluorescence phosphorescence, or inward TADF. So several strategies had been developed, like the phosphorescence relate a heavy metal incorporation, which enhance the spin orbit coupling, and ultimately we get the population over the triplet excited state, and we could get the phosphorescence emissions. And then the next scenario came for the TADF like system. We push the population from uh, triplet to singlet via intersystem crossing. Then triplet annihilation combines from the emission singlet. However, this approach still involve the complex mechanism. The current or latest strategy is the open cell organic radical, involving F1 cell organic radical, which is radical emitter process. So singly occupied molecular orbital possess the doublet excited state. So emission happens D1 to D0, which I already have explained. So one type of transition is possible from D1 to D0. So there is no need to worry about triplet exciter or singlet triplet population distribution. So now the knowledge gap in previous studies suggests that lunar radical system may enhance emission. Homo-LUMO overlap could improve the oscillating strength. However, there is no clear fundamental explanation for why the SOMO radical emits strongly while other remain dark. So existing theoretical models do not fully explain in luminescence mechanism. Now the why the gap matters, because to understanding the emission mechanism is crucial, because radical emitter could eliminate the triplet loss in OLEDs, and this could enable high efficiency without heavy metal or TDF processing. So now, uh, what does this work suggest? Uh, the author did the molecule design or molecule synthesis. So they develop a general molecule design rule for the bright radical emitter. They synthesize new TTM based pyridine pyrrolidine radical, and experiment they experimental demonstrate that the efficiency pure rate device. So now, deviation from the structure, introduction structure. Two minor deviation exist. The introduction include the detailed molecular orbital theory uh, earlier than the typical introduction. A relative long discussion of the radical chemistry literature appear before the specific research objective. And however, these divisions improve the conceptual clarity because understanding the radical luminescence require the electronic structure explanation. Now, uh, the author designed the TTM-based radical because they try to modify the molecular structure to break the alternative symmetry and enhance the oscillating state. So that means the symmetry breaking mechanism is important for this case. They try to show how the symmetry break is important for organic radical system, and they measure the homolumo energy gap by the theoretical calculation. So these are the experiment they have performed. Theoretical experiment they did the DFT studies. The molecular design and synthesis they did, and the spectroscopic characterization by EPR, NMR, and they did the different type of photophysical studies like PLQ, emission spectroscopy, and finally they fabricate the OLED, and they got the external quantum efficiency after the OLED fabrication greater than 12%, which is very significant. And overall, now the comparison of external calculation similarities both highlight the development, though both highlight the development uh, the luminescent radical emitter. Both emphasize uh, the radical design and intensity borrowing mechanism. But the difference is abstracts focus mainly on the theoretical explanation, design rule, and OLED efficiency. But the conclusion provides a broader interpretation and summarize the two key molecular rules, which suggest the non-alternative hydrocarbon oscillating state enhanced the through the intensity borrowing. So overall scientific insight of this paper is the studies provide a fundamental electronic structure explanation for the radical luminescence. The key achievement is uh, establish a molecular design rule for the bright radical. They demonstrate high efficiency rate OLED using the radical emitter, so that doublet emitter can bypass the spin statistic limit. So that's all. Thank you.